progress. Alright. After thinking about lecture 2, I'm starting to think he's ripped off Lavoisier. I mean, I'm sure he expanded on it, but he definitely, this is definitely an extension of Lavoisier. Antony. I really said his name was Antoine. Hell yeah, his name is Antoine. Why not?
Antoine.
Antoine. It is Antoine.
Antoine.
Antoine. Say Anthony. That's like the Americans saying Antoine. I'm probably not going to even finish this.
I wish to draw your attention to water, that we may examine it carefully, especially in relation to the subject, and also with respect to its general existence on the surface of the globe. Now, having previously arranged an experiment for the purpose of condensing water from the products of the candle, my next point will be to show you that this water, and perhaps one of the best means that I can adopt for showing its presence, is to exhibit a very visible action of water, and then to apply that test to what is collected as a drop at the bottom of the vessel. A small piece of potassium shows the presence of water by lighting up and floating about, burning with a violent flame. Will be to show you that this water, and perhaps one of the best means that I can adopt for showing its presence, is to exhibit a very visible action of water, and then to apply that test to what is collected as a drop at the bottom of the vessel. A small piece of potassium shows the presence of water by lighting up and floating about, burning with a violent flame. You see a drop of water, a condensed product of the candle, hanging from under the surface of the dish. I will show you the potassium has the same action upon it as upon the water in the dish in the experiment we have just tried. I will take a drop upon a glass slide, and when I put the potassium to it, you'll see at once, from it taking fire, that there is water present. Now, that water was produced by the candle. Water is one individual thing. It never changes. We can add to it by careful adjustment for a little while, or we can take it apart and get other things from it. But water as water remains always the same, either in a solid, liquid, or fluid state. And now, to go into the history of this wonderful production of water from combustibles and by combustion, I must first of all tell you that this water may exist in different conditions, and although you may now be acquainted with all its forms, they still require us to give a little attention to them for the present, so that we may perceive how the water, when it goes through its protean changes, is entirely and absolutely the same thing, whether it's produced from a candle, by combustion, or from the rivers or ocean. First of all, water, when at the coldest, is ice. Now, we scientists speak of water as water, whether it be in its liquid or solid or gaseous state. We speak of it chemically as water. Water is a thing compounded of two substances, one of which we have derived from the candle, and the other which we shall find elsewhere. Water may occur as ice. Ice changes back into water when the temperature is raised. Water also changes into steam when it's warmed enough. The water which I have before me is in its densest state, and although it changes in condition, in form, and in many other qualities, it still is water. And whether we change it into steam by heat, or whether we alter it into ice by cooling, it increases in volume. In the first case, very largely and wonderfully, and in the second, very strangely and powerfully. For instance, I have this metal bottle into which I've poured a little water into it. I'm converting the water into steam for the purpose of showing you the different volumes which water occupies in its different states of liquid water and water vapor or steam. See what a stream of vapor is issuing from this bottle. You observe that we must have made it quite full of steam to have it sent out in that great quantity. And now, as we can convert the water into steam by heat, we convert it back into liquid water by the application of cold. And if we take a watch glass and hold it over the steam, see how soon it gets damp with water. It will condense until the glass is warm. It condenses the water.
So all of this is just to prove that candles make water as a byproduct. I'm pretty sure that's where they're going with this.
Which is now running down the sides of it. I have here another experiment to show the condensation of water from a vapor state back into a liquid state. In the same way as the vapor, one of the products of the candle was condensed against the bottom of the dish and obtained in the form of water. And to show you how truly and thoroughly these changes take place, I will take this bottle, which is now full of steam, and close the top. We shall see what takes place when we cause this water or steam to return back to the fluid state by cooling it in water. You see what has happened. If I had closed the lid and still kept the heat applied to it, it would have burst the vessel. Yet when the steam returns to the state of liquid water, the bottle collapses, there being a vacuum produced inside by the condensation of the steam. I show you these experiments for the purpose of pointing out that in all these occurrences, there is nothing that changes the water into any other thing. It still remains water. And so the vessel is obliged to give way and is crushed inwards. As in the other case, by the further application of heat, it would have been blown outwards. And what do you think the bulk of that water is when it assumes the vaporous condition? A cubic inch of water will expand to a cubic foot of steam, and on the contrary, the application of cold will contract that large amount of steam into this small quantity of water. Let us now take the case of water changing into ice. We can effect that by cooling the water in a dry ice acetone bath. And I shall do so to show you that when water becomes ice, it changes in volume in an extraordinary way. These bottles are made of cast iron. They're very strong and very thick. I suppose they are each 1/3 of an inch in thickness. I filled this one with water to exclude all air, and I'll screw the plug in tightly. We shall see that when we freeze the water in the vessel, it will not be able to hold the ice, and the expansion within will break it into pieces. No communication will take place, you observe, between the water in the bottle and the ice in the outer bowl, but there will be a conveyance of heat from one to the other. The cold has taken possession of the bottle and its contents. Although the iron was thick, the ice had bursted asunder.
Oh my God.
You see some ice, partly enclosed by the covering of iron, which is too small for them because the ice is larger in bulk than the water. You know very well that ice floats on water. Why? Because the ice is larger than the quantity of water which can produce it, and therefore the ice weighs the lighter and the water is the heavier. To return to our quiet philosophy. We shall not in future be deceived, therefore, by any changes that are produced in water. Water is the same everywhere, whether produced from the ocean or from the flame of the candle. Where then is the water which we get from a candle? I must anticipate a little and tell you. It evidently comes as to part of it from the candle, but is it within the candle beforehand? No. It is not in the candle, and it is not in the air round about the candle which is necessary for its combustion. It is neither in one nor the other, but it comes from their combined action, apart from the candle, apart from the air. And this we have now to trace so that we may understand thoroughly what is the chemical history of a candle when we have it burning on our table. How shall we get at this? I myself know plenty of ways, but I want you to get at it from the association in your minds of what I've already told you. I think you can see a little in this way. I'll use electricity to pull water to pieces. This power supply makes it as though I were applying heat to cause the water to appear to boil. When we separate or electrolyze water into its parts, we get 2 volumes of one gas and 1 of another. The gases produced are not steam. Steam is condensable into water, and when you lower the temperature of steam, you convert it back into fluid water. As you know, water is liquid at room temperature. Notice that this gas, which I've collected, does not become a liquid. I will take another test and apply it to this gas. If I now apply a light to the mouth of the test tube,
He's going a little fast. All right.
it ignites with a slight noise.
Whew.
That tells you that it is not steam. Steam puts out a fire. It does not burn. But you saw that when I had in this test tube burnt, we may obtain this substance equally from water produced from the candle flame as from any other source. Here is a vial full of the same gas. I will show you something most interesting. It is a combustible gas, but it is also less dense than air. Steam will condense. This body will rise in the air and not condense. Suppose I take another vial, empty of all but air. If I examine it with a flame, I shall find that it contains nothing but air. I will now take this vial, full of the gas that I am speaking of, and deal with it as though it were a light body. I will hold both upside down and turn the one up under the other. And now, what does the vial contain that had the gas procured from the steam? You will find it only contains air. But look. Here is the combustible substance which I have poured out of the one vial into the other. It still preserves its quality and condition and independence, and therefore is the more worthy of our consideration as belonging to the products of candle. This is what we get from water, the same substance which is contained in the candle. Let us now trace this.
See the vial.
With it as though it were a light body. I will hold both upside down and turn the one up under the other. And now, what does the vial contain that had the gas procured from the steam? You will find it only contains air. But look. Here is the combustible substance which I have poured out of the one vial into the other. It still preserves its quality and condition and independence. I have poured procured from the steam and turned the one up under the other. And now, what does the vial contain that had the gas procured from the steam? You will find it only contains air. But look. Here is the combustible substance which I have poured out of the one vial into the other. It still preserves its quality and condition and independence, and therefore is the more worthy of our consideration as belonging to the products of candle. This is what we get from water, the same substance which is contained in the candle. Let us now trace distinctly the connection between these 2 points. This is hydrogen, a body classed among those things which in chemistry we call elements, because we can get nothing else out of them. A candle is not an elementary body, because we can get carbon out of it. We can get this hydrogen out of it, or at least out of the water which it supplies. And this gas has been so named hydrogen because it is that element which, in association with another element, generates water. This hydrogen is a very beautiful substance. It is so light that it carries.
And hydrogen and oxygen were named so by Antoine Lavoisier. 75 to 100 years before these lectures-ish.
Carries things up. It is far lighter than the atmosphere, and I dare say I can show you this by an experiment. Here is our tank of hydrogen, and here are some soap suds. I have a rubber tube connected with the hydrogen tank, and at the end of it, a plastic pipe. Now, I could blow bubbles with my breath, or blow bubbles by means of the hydrogen. You observe how the bubbles fell downwards when I blew them with my warm breath, but notice the difference when I blow them with hydrogen. It shows you how light this gas must be in order to carry with it not merely the ordinary soap bubble, but the larger portion of a drop hanging to the bottom of it. I can show its lightness in a better way than this. Larger bubbles than these may be so lifted up. Indeed, in former times, balloons used to be filled with this gas. Water also contains oxygen. Oxygen, as you will immediately imagine, exists in the atmosphere. For how should the candle burn to produce water without it? Such a thing would be absolutely impossible and chemically impossible without oxygen. Now, as regards this very property of oxygen supporting combustion, which we may compare to air, I'll take a piece of candle to show it to you in a rough way, and the result will be rough. You see the combustion in air. How will it burn in oxygen? I have here a jar of oxygen for you to compare the action of this gas with that of air. See how brightly and how beautifully it burns. Is it wonderful how great the supporting powers of oxygen are as regards combustion? But it does not affect merely the combustion of hydrogen or carbon or the candle, but it exalts all combustions of the common kind. We must now, for a little while longer, look at it with respect to hydrogen. I'm now about to set fire to oxygen and hydrogen mixed in the proportion in which they occur in water. Here is a vessel of soap bubbles made with 1 volume of oxygen and 2 volumes of hydrogen, exactly the same nature as the gas we obtain from electrolysis. I will take a bubble in my hand, and you will perhaps think I'm acting oddly in this experiment, but it is to show you that we must not always trust to noise and sound, but rather to real facts. This oxygen united with the hydrogen, as you saw by the phenomena, and heard by the sound with the utmost readiness of action, and all its powers were taking up in its neutralization of the qualities of the hydrogen. So now I think you will perceive the whole history of water with reference to oxygen in the air from what we have said before. Why does a piece of potassium decompose water? Because it finds oxygen in the water. What is set free when I put it in the water? It sets free hydrogen, and the hydrogen burns. But the potassium itself combines with oxygen, and this piece of potassium, in taking the water apart, the water you may say derived from the combustion of the candle, takes away the oxygen which the candle took from the air, and so sets the hydrogen free. And even if I take a piece of ice and put a piece of potassium upon it, the beautiful affinities by which the oxygen and the hydrogen are related are such that the ice will absolutely set fire to the potassium. It produces a sort of volcanic action. It will be my place, when next we meet, having pointed out these anomalous actions, to show you that none of these extra and strange effects are met with by us, that none of these strange and injurious actions take place when we are burning not merely a candle, but gas in our homes or fuel in our fireplaces, so long as we confine ourselves within the laws that nature has made for our guidance.
Because I thought hydrogen was named for being non-burnable. I guess that was more the carbon dioxide. That's from my hit study of Lavoisier. I got to restudy. I know hydrogen's flammable, but I thought it wasn't. Hindenburg, hydrogen, not helium. Dude, this is straight a ripoff of Lavoisier. Come on. It's just, presented nicely. It's his own thing. It's cool. It's cool. It's cool. It's cool. Creative rewriting. It's 100 years. It's outside of Creative Commons. I just wish he would have attributed. Maybe he didn't even know. Maybe it was teachers of his. All right. We're going to do lecture 4.